Good day, I am Fiona Grace Cajas, a member of Group 4, and this presentation covers protection coordination in power systems. When we talk about protection, we are referring to power system protection and how coordination plays a role in protecting electrical systems. In this video tutorial, we will address two main questions. First, what is coordination? And second, why is coordination necessary? So now, let's talk about what we want plainly. What we want is number one, to reduce exposure and isolate a problem or an outage. This is pretty simple to grasp. We don't want the outage to cascade. The second thing we want is to limit the duration of a problem or an outage. We don't want an outage to last longer than it has to. Number three, we want to minimize the actual problem. And what I mean by that is to actually minimize equipment damage. This is what we want from our electrical system, and coordination is going to help achieve it. It's really important to keep in mind that electrical systems must be designed to prevent human injury. So the number one priority should be safety. If we were to summarize coordination in simple words, it would be coordination is essentially to minimize and isolate the problem so the duration of an outage is minimal. Let's quickly give an example of this. Suppose that we work at an industrial facility. In this facility, we might have a generator that's generating voltage, we might have an incoming line from a utility or the grid, or we may have some external source. Suppose that we have a breaker on the high side of a step-down transformer. Suppose that the generator generates voltage at 12.4 kV and the step-down transformer steps it down to 4.16 kV, and then it goes to the 4.16 kV bus. On that bus, let's say we have a tap, and this tap is fused and it's going to a motor. This bus here is 4.16 kV. Then we have another tap and another motor. Keep in mind that this right here is a fuse and this right here is a breaker. Suppose that we have another step-down transformer that's protected by a breaker. But that transformer steps the voltage down from 4.16 kV to 480 volts. And we have another bus that's the 480 volt bus and taps off the 480 volt bus, which are fused, that go to our auxiliary motors or auxiliary equipment. Then suppose we had another step-down transformer that was protected by a breaker that steps down from 4.16 volts to 208 volts. And here, we are feeding all the outlets of our facility. So a problem can be anything, right? A problem that causes an outage. It could be various types of short circuits. It could be overloads, harmonic problems, insulation failure, lightning, loss of synchronism, or simply human error or natural disasters. So a problem is essentially an abnormality that's not common or normal. In our protection coordination, it's supposed to do these three things. It's supposed to reduce the exposure and isolate the problem. It's supposed to limit the duration of the problem. And it's supposed to actually minimize the actual problem so the damage is minimal. Let's see how that works. Suppose that we had a fault or any sort of problem on this motor. We should expect this fuse right here to number one, reduce the exposure of this problem. So reduce the problem area, and it should also isolate the problem area. Number two, it should limit the duration of the problem or the outage. And number three, it should minimize the problem. So suppose that this fuse does not isolate the problem. What's going to happen? Well, the next upstream device, which is this breaker, we should expect this breaker to isolate the problem. But what happens if this breaker isolates the problem? Well, what was a single problem on this single motor has now affected everything downstream. It has affected all the motors that are off of this 4.16 kV bus. It has also affected the 480 volt bus and also affected the 208 volt bus. So that's what we call a miscoordination. It did not coordinate properly, which means that the three rules were not applied. The miscoordination does not fulfill or achieve rule number one. A miscoordination does not achieve rule number two, and miscoordination certainly does not achieve rule number 3. So to put it very simply, coordination minimizes and isolates the problem so the duration of an outage is minimal.
Hello everyone, this is Jaime, and this time I will discuss about the Power Systems Protective Coordination Study Part 2. In Part 1, Fiona discussed about why coordination was needed. In Part 2, I will discuss about the different components of a power system and the reason why coordination works. We have a utility source generating power at 13.8 kilovolts, which is feeding a 1 MVA transformer. The transformer then steps the voltage down to 4.16 kilovolts, which feeds a downstream 4.16 kilovolts bus. There's also a 100 amp breaker, which we will name breaker A. There's another 4.16 kilovolts emergency generator, which feeds the 4.16 kilovolts bus through a tie breaker. We also have a few medium voltage motors connected to the 4.16 kilovolts bus through feeder breakers. Additionally, we have a 20 amp fuse, which is serving as a feeder. This fuse is feeding a 100 kVA transformer, which steps the voltage down further from 4.16 kilovolts to 480 volts. We also have a 120 amps breaker, which we'll name breaker B, which is connected to a 480 volts bus. This 480 volts bus is feeding a low voltage motor through a third breaker, which we'll call breaker C. Before we talk about intricacies of how coordination is actually performed, let's first understand the general structure of this power system under normal operating conditions. The tie breaker connected to the generator bus would be open and interlocked as the system is powered by the utility bus through the utility transformer. If we look at the sizing of each breakers, we can clearly see that the highest rated breakers are connected to the upstream 13.8 kV bus, and the second highest rated breakers are connected to the 4.16 kV bus, and the third highest rated breakers are connected to the 480 volts bus. Intuitively speaking, we should typically expect upstream breakers to be greater than the downstream breaker, for which we'd like to coordinate with. If breaker C is sized at 80 amps, then we should expect breaker B to be greater than 80 amps. As expected, breaker B is rated at 120 amps in our example. And if we consider breaker A, which has a rating of 100 amps at 4.16 kilovolts, then breaker B should typically be sized smaller. Again, breaker B is rated for 120 amps at 480 volts. If we compare both breaker ratings at a common voltage, the difference is much greater. So to summarize it all, as a rule of thumb, we should typically expect breaker size in reference to their downstream or upstream breakers. In part 3, we shall talk about the goals and strategies of protected device coordination.
Pioneer here, and I'll be discussing the primary goals of coordination and the strategies involved to make it work. There are two primary goals associated with coordination. The first one is to ensure equipment protection. This could be a cable, a motor, transformer, generator, or static load. Through coordination, we can achieve multiple layers of protection. We can also coordinate these layers so the fault or abnormality are localized to a zone. This ensures continuity of power to the rest of the system, with the abnormality being isolated to its particular location. We will be discussing this in more details as we continue this series. Before we talk about how to actually achieve coordination, we must first consider the strategies involved. There are two types of characteristics which we can use to coordinate the protective devices in a power system. The first one is the definite time characteristic, which defines a fixed time delay before the tripping action of the protective device. To demonstrate this concept, let us consider a facility with a 50 kVA 60 amps static load percent on the load end of the 480 volts bus. It is being supplied power through a 480 volt cable from the upstream bus. As discussed by Bsee, all breakers should be stated at some percentage above the full load amperes of the downstream load. Breaker C is rated 80 amps at 480 volts, breaker B is 120 amps, at 480 volts and brake array is rated 100 amps at 4.16 kV. Keep in mind the voltage difference between brake array and breaker B. Let's consider an abnormality occurring at the load terminals beyond breaker C. This abnormality causes the current to suddenly increase beyond the normal loading levels. Since breaker C is directly connected to the load, we shall require it to have the fastest tripping time to ensure fault localization. Breaker C is given a definite trip time of 0.3 seconds, so if the abnormal current is above the trip rating of the breaker, which is 80 amps, and the current remains for at least 0.3 seconds, then breaker C will trip to isolate the abnormality. To achieve coordination with the upstream breaker using definite time characteristics, we would need to add some delay to brake AB that is greater than breaker C plus some margin. Suppose this margin was 0.2 seconds. This means that breaker B will have a definite time delay of 0.5 seconds. If there is an abnormally high current beyond breaker B that is greater than the trip rating of the breaker, which is 120 amps, and this abnormal current remains longer than the definite time delay of 0.5 seconds, then breaker B shall trip to localize the abnormal area. Please note that if the abnormally high current was beyond breaker C, then breaker C should isolate the abnormality. Since it has definite time delay of only 0.3 seconds, if the abnormality is between breaker B and breaker C, then breaker B will isolate the abnormality with a time delay 0.5 seconds. Following this design, let's select a definite time delay of 0.7 seconds for brake array. Similar operations now occur between brake array, breaker B, and breaker C. With this strategy, we have achieved some level of coordination. Additionally, we have multiple layers of protection. If breaker C does not trip and isolate the fault for some reason, then we should expect breaker B to trip with 0.5 seconds of delay. This is a simple strategy with some benefits, especially for abnormality at low current levels. The advantage of the strategy occurs with high current levels if we consider a three-phase fault at the 4.16 kV bus which produces an abnormally high current. This strategy may not provide good protection because this strategy uses definite time delay, and to make coordination possible, each layer of protection has some delay. We should expect the highest layer of protection to have the most delay. This is true in our case as well because brake array will wait 0.7 seconds before tripping for the high fault current. If the fault current is high enough, it could result in possible damage to the 4.16 kV bus, and a power blackout could occur, disrupting power to the other loads downstream of the bus. This example highlights a major flaw of using definite time characteristics to achieve breaker coordination, which brings us to another more useful strategy. This strategy involves the application of inverse time over current characteristic, which make it possible for the breaker to vary its delay time directly with the amount of abnormal current. This will be discussed in more detail to the next reporter.
So, hi everyone. So, my name is John Reno Flores. I am a electrical engineering student, Bsee 4. For today's video, I will discuss Powers System Protective Device Coordination Part 4. So, in Part 3, we talk about the primary goals of coordinations and the definite time characteristic strategy. In Part 4, we will discussing the inverse time characteristic strategy and how we can use it to achieve coordinations. Inverse time characteristics are used to define a time delay which varies inversely with the amount of current available. As current goes up, the time delay goes down. Similarly, as the current goes down, the time delay goes up. So current and time are inversely related. The protective device performs its tripping actions after the time has been completed. To demonstrate this concept, let us again consider a facility with 50 kVA 60 amp static load as discussed in Part 2. All breakers should be rated at some percentage above the full load amps of the downstream load. Breaker C is rated at 80 amps at 480 volts, and breaker B is 120 amps at 480 volts, and brake array is rated 100 amps at 4.16 kilovolts. The breaker amps rating is much greater when we compare all the breakers at the same voltage level. Let us consider a triple fault of 20,000 amps occurring at the load terminals beyond breaker C. Under nominal operating conditions, we would require breaker C to trip first if the breaker used a defined time characteristic. Breaker C will have a delay time of 0.30 seconds for 20,000 amps per fault. This means that the high fault current remains on the circuit for at least 0.30 seconds. Then breaker C will trip to isolate the fault. If we compare this with the inverse time characteristic, a higher current level will mean a lower time delay. In the case of breaker C, the delay time would be much less than 0.30 seconds. Depending on the inverse time characteristic curve of the breaker, it might trip after 0.10 seconds of the delay. Conversely, however, if the fault current was only 5,000 amps, then the delay time would be greater than 0.30 seconds. To understand how inverse time characteristic can be helpful in achieving coordination, let's consider a fault between breaker B and breaker C. We know that the upstream breaker B has a higher amps value than the downstream breaker C. If we plot both curves on the same axis, we could observe a shift between the two curves. We will now draw a time characteristic curve which can be used to show the tripping characteristic of a protective device. We have the current level on the x-axis and the trip time on the y-axis. For the same value of fault current, the upstream breaker B will have a higher delay time than the downstream breaker C. This is due to the shift in the curves. Breaker C picks up a lower up rating while breaker B picks up a higher in rating. This is one way to achieve coordinations by using inverse time characteristic of the breaker and the breaker amps rating. If we consider a three-phase fault at 4.16 kV plus which produces an abnormally high current, then this strategy would enable us to achieve coordinations. In the same way, for the same value of abnormal current, breaker E would be shifted furthest to the right, since it is a higher amps rating. Breaker C would be shifted furthest to the left, since it has the lowest amp rating. Lastly, B would be in the middle of breakaway and breaker C curves. So in part 5, we will discussing the time characteristic curve.
Hi, I'm Eric Ponte. Power Systems Protective Device Coordination Part 5. In Part 4, we talk about the inverse time characteristic strategy and how we can use it to achieve coordination. In Part 5, we will be discussing the time characteristic curves. Time current characteristic curves are used to show the time taken by the breaker to trip for a range of overcurrent conditions. They define the operating characteristics of a protective device. The x-axis shows the current level and the y-axis is used to show the time taken by the protective device before the tripping action is initiated. To explain this concept, let us again consider a facility with a 50 kVA, 60 amps static load as discussed in the previous parts. All breakers should be rated at some percentage above the full load amps of the downstream load breaker, C. C is rated at 80 amps at 40 volts. Breaker B is 120 amps at 480 volts. Break array is rated 100 amps at 4.16 kilovolts. The breaker amp rating is much greater when we compare all the breakers at the same voltage level. To demonstrate how time current characteristic curves can be helpful in achieving coordination, let's consider a fault between breaker B and breaker C. For this case, let's assume both breakers to be thermal magnetic breakers. We will now plot the curves of breaker B and breaker C on the same axis. We can see that breaker B picks up at a higher amp value while breaker C picks up at a lower amp value. This results in a shift between the curves and allows coordinations. Now that we understand the basics, let's go into more detail and talk about the different regions of a time current characteristic curves for a thermal magnetic breaker. There is a long time region which starts from the pickup amp value. This region includes the protection against overloads from 110 to 120 of the amp rating. There is a fixed, non-adjustable time delay for each breaker, after which it enters the instantaneous region. This instantaneous region could begin from 200 to 300% of the amp rating and is used for protection against high abnormal currents. The instantaneous region has a very small delay of a few cycles, after which the tripping action of the breaker is initiated. This is one way of achieving protection coordination using inverse time characteristic and the breaker amp ratings. However, there is a flaw with using thermal magnetic breakers for coordination purposes. If we look at the curves again, we can see that the instantaneous regions of breaker B and breaker C are overlapping after a certain current level. Let's say this level is at 10,000 amps. What this means is that for any fault current above 10,000 amps, there is a high risk of both breakers tripping simultaneously. This will result in a power blackout on the 480 volts bus. Bus type of overlap is particularly true for thermal magnetic circuit breakers, which have a fixed amp rating, some instantaneous rating adjustment, and fixed curve. This will be discussed in more detail later in the solution. To eliminating this overlapping region lies with the use of breakers with electronic trip units. Their operating characteristics are highly adjustable for ensuring better protection coordination. In part 6, we will discussing the operating characteristic of electronic circuit breakers.
And now, we will be discussing the TCC curves of electronic trip units and how they can help us in achieving protective coordination. To demonstrate how TCC curves can be helpful in achieving coordination, let's consider a fault at the load terminals of breaker C. This time, however, we will assume breaker C to be thermal magnetic and breaker B to be a breaker with an electronic trip unit with adjustable settings. We will now plot the curves of breaker B and breaker C on the same axis. As was established previously, breaker B picks up at a higher amp value while breaker C picks up at a lower amp value. This results in a shift between the curves and allows coordination. For an electronic trip unit, there is a long time region which starts from the pickup amp value. This region includes protection against overloads. The pickup starts from 110 to 120% of the amp rating. There is an adjustable time delay after which it enters the short time region. The short time region is used to define another adjustable pickup value along with an additional delay setting. These adjustable settings help achieve coordination with downstream devices. And finally, we have the instantaneous region that can trip the breaker very quickly, requiring only a few cycles. Both the short time and instantaneous regions are for protection against high fault currents. In order to better understand the concept of short time, let us recall the time current curves which were demonstrated by Aaron. One of the highlights was a floor in the instantaneous region of the curves, which overlap after a certain current level, resulting in both breakers tripping simultaneously. Let's say the maximum fault current on the terminal of the loads is 10,000 amps. For this case, we want breaker C to trip first. For all fault levels at 10,000 amps and below, we would want breaker B to only trip for operational failure of breaker C or faults on the 480 volt bus. This is where the short time region comes into play. We will use this region to define an additional delay time of 6 cycles, which would prevent breaker B from tripping simultaneously with breaker C. With this scenario, breaker C protects the load up to the maximum fault level on the terminals of the load. It also protects against overloads. Breaker B protects the 480 volt bus and acts as a backup protection device for breaker C. We have achieved good coordination for this particular scenario. This concludes our discussion on TCC curves and their role in achieving protective coordination.